Well, aloha everyone. Today we're going to talk about the kinematic equations. Now, what are the kinematic equations? Well, in order to know that, first we have to understand the kinematic variables. There are 5 variables that we've learned so far that are going to be very important in your ability to calculate anything. And they are v initial, v final, acceleration, displacement. These are all vectors, by the way. And the one that isn't a vector is time. Now, on some formula sheets, you might see them written like this. Instead of v initial, they write v naught. Instead of v final, they write v. Acceleration is the same. Sometimes instead of distance, you're going to see something x minus x naught. And that's going to say the final x position minus the initial x position. What does this mean? Well, x minus x naught is just going to be the displacement of the object. And they will use time. Sometimes people will use a delta t here, which just means how much time elapsed in the process. If you assume that your initial time is 0, then you can just use the time. Okay, so now that we know these 5 kinematic variables, there are 4 kinematic equations that are made up out of these 5 variables. And the kinematic equations allow you to relate things like distance to things like acceleration, things that don't naturally have a definition that incorporates the two. But it turns out that there is one caveat about this, and that is these equations are going to assume constant acceleration. That means that the acceleration is not changing as these things are happening. So, these equations are going to assume that there's a constant acceleration of an object. So an object that's falling without air resistance would have constant acceleration. A car that's speeding up might have constant acceleration for a while, but as it approaches its top speed, its acceleration starts to change, and then these equations will no longer be valid. The moment something changes the acceleration, the moment the equations all change. So you need to be very careful when you think about this. Okay, so what are the kinematic equations? Well, the first one I think is kind of obvious. And it's actually kind of a sad one. The first one is really just kind of a modified version of our definition of average velocity. And I'll tell you what, I'll show you how we get the first equation. We start from here. V average equals d over t. These are vectors. So this is average velocity is equal to displacement divided by time. Okay, we know that. We also know if you're accelerating at a constant rate, your average velocity is going to be v initial plus v final and divide by 2. Just like you average any two numbers. Add them together and divide by 2. So, v initial plus v final divided by 2, vector there, is going to be equal to d over t. D is a vector. Okay, so you probably won't see it like this. You'll probably see it rearranged a little bit, and it'll look like this. Vi plus vf over 2, vector there. I guess you don't need those parentheses. They're just serving double purpose. This entire thing times t is going to be equal to your displacement. This is the first kinematic equation. And all it is really is the definition of average velocity. That's all it is. And we plugged in what average velocity means and then moved it around a little bit. So there's your first kinematic equation. The second kinematic equation, well, that one comes from the definition of acceleration. What do I mean by that? Well, you might remember that acceleration is equal to the change in velocity divided by the time, or change in time perhaps. Delta there, not a huge deal. Okay, so we'll assume that we start at time is equal to 0, in which case we will get v final minus v initial is the change in time, is the change in velocity, sorry, divided by time. So that's a v, that's a vector, that's a vector, that's a vector. So what does our second kinematic equation look like? Well, usually it's not written this way. Usually it's rearranged as well. And it's rearranged like this. V final vector is equal to V initial vector plus A vector times t. This is the second kinematic equation that you will often see. This was the first one. So we have kinematic equation 1 is about average velocity. Kinematic equation 2 is really just the definition of acceleration moved around. Kinematic equation 3 takes a little bit of calculus to derive, so I'm not going to. Oh, I guess you can do it with some geometry, but it's probably not worth it. I'll just wait until you're in calculus and I'll show you how it is then. But in any case, what does kinematic equation number 3 look like? Well, it's going to be this. D equals V initial t plus 1/2 a t squared. That's a vector, that's a vector, and that's a vector. So this one is sort of talking about what happens when you have both velocity, an initial velocity, and an acceleration at the same time. How far is an object going to go? And finally, our fourth kinematic equation kind of combines some of the other ones, and you can derive it, but that'll be left for an exercise for your students to do. So it's going to look like this. V final squared vector equals V initial squared vector plus 2a vector d vector. That's not a very good vector sign. D vector. There we go. Kinematic equation number 4 right here. Now, sometimes they won't just call these the kinematic equations. Some people like to call these the uniformly accelerated motion equations, which are to remind you that acceleration has to be constant. So, there are 5 kinematic variables and 4 kinematic equations. In order to apply any of these kinematic equations to solve anything, you must know at least 3 of the variables. You must know at least 3 variables. And if you know 3 of the variables, then you can pick an equation that will allow you to solve for 1 or 2 of the others. In fact, if you know any of the 3, you can, assuming you have access to all 4 kinematic equations, you can solve for the other 2. So you must know 3 variables to solve for the other 2. Okay, so class, how many kinematic variables are there?
5.
And how many kinematic equations?
4.
You must know at least
3.
in order to find the other
2.
which makes for... surprise, I borrowed that from a colleague over at Flipping Physics. If you want to find out the answer, go check out his page. So let's see an example of using kinematic equations in real life.
So here I have a dynamics cart on a track. And I've intentionally made this side a little bit higher than this side. So when I let it go, it will accelerate in that direction. I'm going to start this dynamics cart at the 20 centimeter mark. and it's going to run over here to the end stop. When it hits the end stop, it will be at 98 centimeters. As I let it go, you'll notice that it will accelerate down the track. I'm going to time it. And when I time it, I will be able to have one of the kinematic variables. I can figure out the distance that this cart travels, and I also know that the initial velocity will be 0. So let's try this. We're going to start at the 20 centimeter mark and begin. Stop. 4.05 seconds.
All right, so if we need to solve anything, we're going to start by drawing a diagram. We have the track here. I guess it only had a stop on one end. We had our car on top of this track. And we know it started at the 20 centimeter mark. And it ended over here at the 98 centimeter mark. Which means that what is the distance or displacement between these two things? Well, d vector is equal to, well, 98 centimeters minus 20 centimeters will tell us it went 78 centimeters, which is the same as 0.78 meters to the right. And it also becomes a little bit more important that we take the time to define which way we're going to call positive. In this case, since our numbers are increasing to the right, we are going to call that way to the right positive. So I'm going to tell everyone with that arrow that to the right is positive. Okay, so we know D. We also know V initial. V initial was 0 meters per second because we started it from a stop. We don't know what V final is. We don't know the acceleration, but we do know the time. The time was equal to 4.05 seconds. So let's say we were asked to find, first of all, the acceleration of this car. What is the acceleration of the car? Well, in order to find that, I need to use a kinematic equation. And I'm going to look at my kinematic variables. And I see that I have a distance, I have a v initial, I have a time, and I'm looking for acceleration. So I'm going to look for a kinematic equation that has those three known variables and the one unknown variable that I'm not looking for. You'll notice we haven't said anything yet about v final. So we're looking for the equation that does not have a v final in it. If you look at it, it's going to end up being this one. D equals v initial t plus 1/2 a t squared. D is a vector, v initial is a vector, and a is a vector. All right, so the first thing we need to do with this equation is move it around. We're looking for the acceleration. So we need to get a by itself on one side of the equation. So remember, when you're solving an equation, you're going to do the order of operations backwards. So first undo any pluses or minuses, then undo any multiplication or division, and then at the end undo exponents, and then parentheses. So the first thing I'm going to do is I'm going to move the vi times t. It's added here, so we're going to subtract it. So this is going to be minus vi times t and minus vi times t. So on this side, on the left side, I'm going to get d vector minus vi times t is equal to 1/2 a vector t squared. All right, the next thing I need to do is I need to get rid of the 1/2. To get rid of a fraction, I multiply by the reciprocal. So I'm going to multiply both of these sides by 2. So times 2 and times 2. Bam, that part goes away. And we're left with 2 times the quantity d minus v initial times t, vector there, is equal to a t squared. The final step is going to be to undo the multiplication between a and t squared. So I'm going to divide both sides here by t squared. So divided by t squared and divided by t squared. Bam, that goes away. Now, there's something you need to be careful about here. A lot of people see this t here, or t squared there, and this t here, and they will say, oh, don't they at least partially cancel? And the answer is no. Why? Well, if there's ever a plus or a minus in a fraction, that's going to mess up the ability for things to cancel nicely. In order to get a t to cancel here, we'd have to be able to factor it out of that expression. And in this case, we can't because d is not multiplied by t. So we can't get a t to cancel in this case, so it's just going to stay like that. So what does our final equation, once we manipulate it, look like? Well, it looks a little bit messy, but it's this. 2 times d minus v initial t over t squared is equal to a. All right, let's plug in some numbers. 2 times, what was the distance? It's way back up here. Distance was 78 centimeters or 0.78 meters. So 0.78 meters minus, what was v initial? Well, v initial was 0 meters per second. Times, what was our time? 4.05 seconds. All divided by 4.05 seconds squared is equal to, one thing to save you some strokes on your calculator, you'll notice this 0 is being multiplied by 4.05. When you multiply 0 by anything, that becomes a 0. And so we don't need to worry about that whole piece because subtracting 0 doesn't do anything. So really, I can simplify this down to something like this. 2 times 0.78 meters divided by 4.05 seconds squared. Now all we have to do is type that into our calculator, and we find that the acceleration is 0.951. What are my units? Well, they're actually given to you right here. There's a meters on top. And in the denominator, there's a seconds that's being squared. So over seconds squared. Or maybe we call it meters per second per second. I think I missed a 0 there. It's not 0 point that. I think it's 0. Let me use the right color here. 0.09510 something. Let's call it 0.095. So this is equal to 0.095 meters per second per second. That was the acceleration of the cart. But what if I wanted to know the final velocity of the cart? What is the final velocity? Well, in order to solve this problem, I can use 2 of the equations earlier. Now that I know 4 of the 5 kinematic variables, there are 2 equations that will work here to find the final velocity. And they are equation number 2, which says this: V final is equal to V initial plus A times T. And equation 4, V final squared is equal to V initial squared plus 2AD. I can use either of these equations to solve for V final, because I know all the other variables that are in each of these equations. If ever you have a choice between using two equations, always pick the one that's easier. There'll be less error, there will be less chance of mistakes, and even there will be less chances of transcription errors. So because of that, in this case, looking at these two equations, it looks to me like this equation is going to be easier. Because all I have to do is plug in the numbers. I don't even have to manipulate it. So I'm going to use kinematic equation number 2 here. And here's what we're going to see. V final is equal to, V initial is 0 meters per second, plus acceleration we just found up here in this step, 0.095 meters per second. By the way, a quick note here. If you're using your answer from the previous step to find the answer to another step, try and always use the number that's in your calculator. Don't use the rounded number we have here. Try and use as many digits as your calculator will give. That'll give you a little bit less rounding error, because if you round every step, you're going to get farther and farther off from the actual number. So don't use the rounded number, keep the exact number in your calculator, and just use that when you use it for the next step. I'm going to write 0.095 here, but when I actually do it, I'm going to be using 0.0951074533132, and who knows how many other digits my calculator has in it. But I'm going to use that exact number when I go back here. All right, then I need to multiply by the time, and the time is 4.05 seconds. V final is going to be equal to, multiply by 4.05 seconds, and I get 0.385 meters per second. By the way, both of these answers are going to be vectors, which means in my diagram above, this was all to the right, so this is to the right. And V final is also to the right. Now you do have to admit, the algebra got a little bit messier there. But it's all right, and we'll get used to using that algebra with practice. What do you say we try another one? Here we go. Let's imagine that we have, let's make it a truck today. So here's a truck, like a semi-truck. All right, here's our semi-truck. And our semi-truck starts off traveling this way with an initial velocity of, let's make it 30 meters per second. And over here, there happens to be a red light. So this semi-truck is going to begin to slow down. And let's say that he is going to travel a distance of 300 meters as he slows down. Well, from just this scenario alone, I can't solve anything. Because, remember, how many variables do you need in order to solve any problem? You need 3. So because of that, we need one more piece of information. And even though it's not stated, you can make an assumption here. Your assumption is that if this is a red light, he's going to slow down such that his final velocity is going to be 0 meters per second. Letter A, I'm going to ask, what is his acceleration? What is the acceleration of this vehicle, of the truck? Well, I look at my kinematic variables that I have. In fact, it's not a bad idea to start by filling out a chart that looks like this. Distance, or displacement actually, v initial, initial velocity, v final, for final velocity, a for acceleration, and t for time. And I'm going to plug in the pieces that I know into this table. So I know v final is going to be 0 meters per second. I know v initial is going to be 30 meters per second. I know the displacement is 300 meters. By the way, that's right. V initial is also to the right. And 0 meters per second doesn't need a direction because he's not going anywhere. Okay, so I look at those and I say, I need acceleration. So I look for an equation that has those four variables. It's got to have a d in it. It's got to have a v initial in it. It's got to have a v final in it. And since I'm looking for acceleration, it also has to have an a. It should not have a t. So that's going to be kinematic equation number 4, which looks like this. V final squared equals V initial squared plus 2AD. Vector, 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 and vector. I need to solve this equation for acceleration. So, first thing I'm going to do is I'm going to subtract V initial from both sides. Now, I'm not going to show the intermediate steps every single time, and I don't expect you to show me that you're subtracting V initial every time either, V initial squared, I don't need to see that. Certainly, if ever I go too fast and you can't tell what I'm doing, be sure to ask me. But I'm just going to show you what happens after that step. It's going to turn into V final squared minus V initial squared equals 2AD. Vector, 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 and vector. Now I'm going to divide by 2d. And our final answers, or our final formula, is going to look like this. V final squared, vector, minus V initial squared, vector, divided by 2d. It's a terrible d. Vector is equal to a vector. So there is my final equation that has been manipulated. Now all I need to do is plug in some numbers. So V final is 0 meters per second. Square it. Minus V initial is 30 meters per second. Square it. Divided by 2 times the displacement is 300 meters. Let's see, this is equal to, well, 0 squared is 0. 0 minus, let's see, 30 times 30 is 900 meters per second squared and squared, because both of those got squared, divided by 2 times 300 is 600 meters. All right, this is equal to, my answer, you'll notice on top, this is negative. 0 minus 900 gives you a negative number. In fact, it's negative 900. Negative 900 meters squared over seconds squared divided by 600 meters. This is equal to, well, meters here and meters, one of them goes away. So I know my units are going to be meters per second, which is good because what am I finding? Acceleration. So it makes sense that we would have units of meters per second. All right, we can reduce 900 over 600, bam, bam, and bam, bam, which is 9 over 6. We can divide both of those by 3 over 3 over 3, and that's going to reduce to 2, and that's going to reduce to 3, which is 3 over 2. 3 over 2 meters per second, or maybe you'll just have A equals 1.5 meters per second. And it's negative. Why is it negative? Well, we didn't actually say it was here, but everything to the right was positive. That means my acceleration is going to be 1.5 meters per second. It's going to be negative, and negative indicates to the left. Okay, so we have our acceleration. Now all we need is to find our time. So part B. What is the time it takes to stop? So as this truck is coming to a stop, how long does it take from the moment he applies the brakes to the moment he stops? How many seconds? Well, in this case, again, looking at the kinematic equations, we can see that it's going to take, we have two equations that will solve this. One of them is kinematic equation number 2, which looks like this. V final equals V initial plus A times T. The other one, put in my vector signs here, the other one is going to be kinematic equation, not 3, 4. Kinematic equation number 4, which is going to be, no, I lied, it was 3. Kinematic equation number 3, D equals V initial T plus 1/2 AT squared. So both of these equations will solve our problem. We can find the time using either of these equations. However, one of these equations is going to be significantly easier than the other. You'll notice solving for t here is going to be a mess. We've got a t squared here, we've got a t there. That means this is, the only way we can solve this is using a quadratic equation. But I can solve this for t very easily. So because of that, guess what we're going to do? We're going to solve kinematic equation number 2 for t. Solve for t. When we solve this for t, we are going to get V final minus V initial divided by A should be equal to t. If that was a little bit fast for you, go through the math and make sure you end up in the same place I did. Let's plug in some numbers. Let's see, what was V final? V final was 0 meters per second. 0 meters per second. Minus V initial was 30 meters per second. So minus 30 meters per second. Divided by, what was his acceleration? It was negative 1.5 meters per second. Negative 1.5 meters per second. And this is equal to, you can either type this into your calculator or you can just do it the longhand way. Either way is fine. This is going to be negative 30 meters per second divided by negative 1.5 meters per second. Negative and negative create a positive. And 30 divided by 1.5 is going to be it's going to be 20. What are my units? Well, I have meters here, canceling meters there. I have seconds here, canceling one of those. and I'm left with seconds on the bottom of the bottom, which means it comes up to the top, and I get 20 seconds. So it's going to take this semi-truck 20 seconds to come to a full stop. So that's at least a start on kinematic equations. There's a lot more to it. I mean, the basic equations don't change, but solving for the different variables is going to take practice. But it's all right if you feel a little bit overwhelmed with the algebra right now. We'll get more practice to work with them as time goes on. And I promise you, we're going to be using these kinematic equations for a long time. So you'll have plenty of practice to get really good at these. Mahalo for watching, and see you next time.